Hello, assalamu alaikum everyone. Welcome to today's lecture. Today we'll be discussing a very important topic which is really important for your solid mechanics course as well as for some instances in fluid mechanics. So trapezoidal load distribution is a kind of uniformly variable load or varying load, but it can be very difficult for many of us because of its shape. For example, if we have a triangular shape, in that case it's very easier for us to calculate the equivalent force, right? But for trapezoidal load distribution, it's really hard for us for sometimes. So we know for distributed load, in order to get the equivalent load, we need to calculate the area. For instance, here we have the area created by these two forces, which has a height of 50 pound per feet in the right side and 100 pound per feet in the left side. And you can see like force is reducing from the left to right. So and it has created a trapezoidal shape. So in order to calculate the equivalent force, that means we want to change the distribution of the force into one particular force. In order to do that, we need to calculate the area, and after that we need to find the centroid of that object. So now let's move on to this particular problem. If we can solve this problem, I think we will be able to understand the overall scenario here. So as you can see here, we have a load of 100 pound per feet in the left side, and we have 50 pound per feet in the right side. And the total length of this beam-like structure is 9 feet. Now what will we do? We will divide that into two simplified part. One, we will have a triangular shape on the top, and another one we will have a rectangular shape in the bottom. After the division, what we're going to do is we're going to find the equivalent force and the location of the force for the triangle or the rectangle individually. Then we'll sum the forces, like there will be one force acting on the triangle, another one is the rectangle, so we'll be combine them together, and then we'll get a moment to get the location for the combined force, right? So as you can see, our force has been divided into two parts, equally divided. One is 50 pound per feet. How do you know that? Because you can see the right side we have 50 pound feet, and we just drew a straight line from there, right? And as we have like 100 pound per feet, so it has been divided into two equal part. It may not be the same for every cases, but the simplified case, that's why I made this example in such manner. Now we have to find the area of the triangle, because we need to find the equivalent force for the triangle. So we know the area of the triangle is half height times length. So height is here is 50 pounds per feet, and we know the length here, the base is 9 feet. As you can see, after multiplying all those, we are left with 225 pound. Feet and feet are cancelled out. Similarly, for the rectangular case, we will find the area of the rectangle, and we'll get 450 pounds, and the total force will be 675. It's a very basic calculation. So now we need to find the location of the force. We know for triangular cases, it's always 1/3 from the left side. That means where we have the highest peak of the force, it will be near to that position, right? So 9 divided by 3 is 3 feet, so it will be on the 3 feet away from the left side. For the rectangular case, it will be in the middle, because it's a very symmetric shape and everything is symmetric, so we'll get it in the just in the middle. Now what do we need to do is we need to find the moment for the combined forces. Then we'll get a distance from the left side, and the distance from the left side will be the point of action for the combined case, which is the trapezoidal axis. So here we'll find the moment. For example, here we took the moment from on the left side, so this 225 times 3 plus we'll do the 450 times 4.5 equal the combined force, right? Combined force was 675 times arbitrary distance. So if we can solve for the d, we'll get the location of the force of the equivalent force, right? So we can get the d 4 feet. As you can see in the location correctly. You can use it for the pressure prism concept also in fluid mechanics. However, there's one slight thing you need to be worried about, because pressure has to be on a cross section area, right? So in that case you have to be worried about the cross section area. If it's in the unity, you can use this method to calculate the force very easily.